Hello, welcome. Today I'm going to try to solve the Leetcode problem by using minimum spanning tree. And this time I'm gonna use Kruscal's algorithm to solve it. Yeah, it's the same. Number 1584, mean cost to connect all points. I don't need to explain the problem anymore because it's very clear. We just need to calculate the minimum cost by connecting all those points. So this is the minimum spanning tree question. We can use Prime's algorithm or Kruscal's algorithm. I've just solved by Prime's algorithm. Basically, that is the greedy idea with a mean heap. Yeah, so this is the code, and I've already posted a video about it. So the time complexity for this will be n squared log n. And you can check the speed for this time complexity. So this is the Prime's algorithm. Yeah, as you can see, basically that is 1.6 seconds. Now let me go to explain the Kruscal's algorithm for the similar problem. Yeah, so for the Kruscal's algorithm, basically we need to do something like this. Yeah, we need to find all the edges. We put all the edges inside an array and we sort the edges. So according to the weight, according to the distance. So we're gonna sort it. And then we're gonna check one by one. So for example, if this is the shortest, we're gonna connect this one. And if this is shortest, we're gonna connect this one. And then we compare. Yeah, if this is the shortest, we're gonna connect this one. Yeah, so by connecting the points, we can use the unified. Basically, when we are talking about Kruscal's algorithm, it is a unified. Yeah, so now these edges are left and they are not connected, so we just connected it. So yeah, so this is the Kruscal's algorithm. Basically, we need to use the unified to connect all the edges. So while connecting all those edges, we are connecting the minimum spanning tree. So this is actually another way for solving the minimum spanning tree problem. Yeah. Now let me go to the code editor to explain the code. Yeah, basically this is just the template code. So for the unified, so while I'm preparing for solving the unified problem, basically I have two types. So one is the continuous points. I will gonna use the array as my parent array, so it will be list range of n. So there's another case for the unified. Yeah, another template for the unified. It will be a set. Yeah. So if the points or the nodes inside the array is separate, yeah, it is not continuous nodes like 0, 1, 2, 3, 4. Maybe it is like 1, 100, 1000. If yeah, the points are like that. So we're gonna use a dictionary. Yeah, because the dictionary is more efficient than array. So if the points are not continuous. So if it is continuous like our problem, I prefer to use a list. So this is the template for the unified. Basically, we're gonna have find and union. So I would like to write the unified, yeah, unified as a class because I want to keep it separate from my main function. I don't want to put it inside because it is too confusing. Yeah, and I want to keep it consistent and I will not change my template anymore. Yeah, because it's easy to make typos if you type differently for different problems for the unified. Now I just need to solve the problems. So for solving the problem, basically I need to prepare all the points. But this time for Kruscal's minimum spanning tree, we're gonna prepare an edge array. So inside the edge, it's gonna be a distance, and then with 2 points. So the points will be u and v. So this u and v just need to use 2 for loops to find all the points. Like for example, here it's gonna be 0 to 1, 0 to 2, 0 to 3, and 0 to 4. And then I got all the distance. After that, I can use a sort. Because I put the weight at the first index, so I don't need to use a lambda function to control the sort. Yeah, so this means that the edges will be sorted. And then I can just use my unified API. So the UF should be equal to UFN, and the result is my final result. Here I use a as equal to 0 to just let the for loop stop earlier if the as equal to n minus 1. Because if this as equal to n minus 1, it means we've already found the minimum spanning tree, so we're gonna break it. If we don't, it's gonna be much slower. Yeah. So in the main function, we just take out the cost and 2 points. Yeah. If they are not connected, we're gonna connect it, and the edge should plus 1, and the result should plus the cost. Yeah. Let me explain this line of code. So this means if we have 3 points, those 2 points are connected. They are the shortest distance. If we have another point, it's here. And these 2 points, if they are not connected, we're going to connect it. So this is 0, 1, and 2. Now we are going to check 0 and 2. Because 0 and 2 are connected, so from here, we don't need to do anything because they've already connected. So we just go over. Yeah, we just go on to check the next edge. Maybe there is another node. Maybe this node is 3. Yeah. Now we're gonna connect this node. Yeah. But how should we check this node? We're gonna just to check another edge. Maybe there is another edge. Maybe 1, 2, 3. Yeah. If they are not connected, so we're gonna union connected them. Yeah. So it's gonna be like this. This is just to avoid the duplicate. So for 0 and 3, they are not connected, so we are not going to do it. Yeah. Now, if the edge equal to n minus 1, because from here, if we find the minimum spanning tree, because the vertices of the minimum spanning tree will be n minus 1. N is the number of vertices. I mean the edge. The edge for the minimum spanning tree is n minus 1. N is the number of vertices. So from here, I can stop earlier. Now let me submit it. Let's just check the speed, comparing with the Prime's algorithm. Yeah, first of all, the time complexity is still E log E. So E is the number of edges. So if it is the number of vertices, it is n squared times log n squared. Yeah, but the final time complexity will be also the same. Yeah, let me write it here. So the time complexity will be O n squared log n. Yeah, so this is the final time complexity. But this n can be n squared, but it is the order of log n because it's the same. This is why it is a little bit slower, but it's basically it's nearly the same. So if we don't want to use the edge to let it stop earlier, basically we're gonna need to check all the edges. Yeah, if after all those edges are already connected. If the edge has already been n minus 1, we have to check all other edges. Yeah, check, and all other edges will be n squared. So this way it will be much slower. Let's just check the speed. Yeah, as you can see, it is 2.7 seconds. It is much slower than before because we checked all the edges. Yeah, and we can stop earlier when edge equal to n minus 1. So this is the most important part, I think, about the Kruscal algorithm. Basically, when you are comparing, the time is nearly the same. Yeah, this is because this is also n squared log n. Thank you for watching. If you think this is helpful, please like and subscribe. I will prepare more Leetcode problems like this.